All right, this is the second part of chapter 18. So this is 18 part 2. And we're going to pick up with this slide. So what does 95% confidence really mean? Okay, so each confidence interval uses a sample statistic to estimate a population parameter. All right, so in reality, for this bullet point, okay, we're going to use our p hat to approximate population proportion p. And later on, we're going to see, or we can use x bar to approximate mu, our population mean. Now, since samples vary, the statistics we use and thus the confidence intervals we construct will vary as well. So what that means is this p hat will be different depending upon which sample I actually take. So that's kind of a weird thing to think about. Okay, we're using that to approximate a fixed value, our true population p, and this thing's going to vary. Same thing happens with mean. So this differs every time I take a sample, but we're trying to approximate some fixed and unknown value, our true population mean or proportion. So what does 95% confidence really mean? The figure to the right shows that some of our confidence intervals from 20 random samples captured the true proportion, which is the green horizontal line, while others do not. So each of these, so this is one confidence interval, this is another confidence interval. Each of these red dots are p hats. So I take a p hat, I build a confidence interval. This one did not get p. Here's p, the true p. Okay, this one did. Now watch this, there are 20 different confidence intervals. Out of the 20, how many captured them? So it looks like yes, 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 no. That's a no. Those are all yeses, that's a no, and that's a no. So in reality, 17 out of 20 of those confidence intervals captured my true proportion. And if I take 17 and I divide that by 20, that is about 85%. Okay, now that's supposed to equal 95%. Why do you think that's supposed to equal 95%? Because we did a 95% confidence interval. Okay, so of all confidence intervals that I create, 95% of those confidence intervals will actually capture the true p. Okay, so our confidence is in the process of constructing the interval, not in any one interval itself. So that's an important note. An interval will either contain our p or not. Okay, so we don't know what's going to happen. The process of constructing intervals where our confidence comes from. Thus, we expect 95% of all 95% confidence intervals to contain the true parameter that we are estimating. All right, so margin of error, this is certainty versus position. So this is how we construct a 95% confidence interval, CI, okay? We take our p hat plus or minus 2, we'll talk about where that 2 comes from in a second, times our standard error p hat. So we can claim with 95% confidence that the interval contains the true population proportion. The extent of the interval on either side of p hat is called the margin of error. So this whole thing on this side is called the margin of error. Okay? The more confident we want to be, the larger our margin of error needs to be, thus making the interval wider. So if I have a larger interval, that means more values I capture, which means more confident that I am in my answer, in my interval. Okay. Now, we could always get more confidence by making a larger confidence interval. So look at this confidence interval. So this is now a 99.7% confidence interval. So I just simply add 3 units of standard deviation and subtract 3 units of standard error on either side. And I get a really huge margin interval, and I capture even values. And I'm really confident that true p is in there. Now the problem is, yes, I am more confident in my answer, but I'm less precise because I get more different values. Okay. So to be more confident, we wind up being less precise. We need more values in our confidence interval to be more certain. Because of this, every confidence interval is a balance between certainty and precision. The tension between certainty and precision is always there. Fortunately, in most cases, we can be both sufficiently certain and sufficiently precise to make useful statements. So basically, we will almost always in this class be constructing a 95% confidence interval. This turns out to be pretty good. That's about as confident as we need to be. Okay. The choice of confidence level is somewhat arbitrary, but keep in mind this tension between certainty and precision when selecting your confidence interval. The most commonly used confidence levels are 90, 95, and 99%, but any percentage can be used. Now, where did these come in hand? Well, the 2 that's in front of our standard error actually comes from the 95%. Remember, that corresponds from the 68, 95, 99.7 rule. This is 1 standard deviation, 2 standard deviations, and 3 standard deviations, okay? Now, this is a rule that's actually rounded values. If I calculated exactly using a table of technology, we would find that the exact value for 95% is actually 1.96 instead of 2. This 1.96 is what's called the critical value, and we denote that as C star. But for any confidence interval, we can find the corresponding critical value, which is the number of standard errors that corresponds to our confidence interval. Okay, so for example, for a 90% confidence interval, the value would be 1.645. So step 1, what I would recommend doing for confidence level is in the middle of your normal model, draw your confidence area. So for 90%, we want the middle to be 90%. That's how much we want to capture. Now, since this is symmetric, we know that on the outside is going to be 10%. So on this side, it's 5%. And on this side, it's 5%. Okay, so the area over here is really 0.05, and the area here is 0.05. So to calculate this Z star, what you can do, okay, Z star to the negative is going to be inverse norm of the 0.05 area to the left, this area here, comma 0, comma 1. And when you do that, you get negative 1.645. To get this Z star, what you can simply do is do inverse norm, okay, of 0.95, the total area, 90% and 0.05, comma 0, comma 1, and you are going to get 1.645. And you can do this trick for all confidence intervals. So I would just recommend drawing the normal curve. The middle is your confidence interval. Find the areas on the outside, and then just do the underneath. So remember, in general, the inverse norm, the input is going to be area to the left, comma mean, comma standard deviation. Since this is a Z, we know that's always going to be 0 and 1, or a Z score, basically, the number of standard deviations. All right, example 5. So Pew Research in November 2011 polled a random sample to 799 US teens about internet use. 49% of those teens reported that they had misrepresented their age online to gain access to websites and online services. So part A. All right, so find the margin of error for this poll if we want to be 95% confident in our estimate that the percentage of Americans, teens misrepresented their age online. Okay, so confidence interval is p hat plus or minus the margin of error, which translates to p hat plus or minus the Z star times the square root of p hat q hat over n. So for part A, it wants us to calculate the margin of error, which is just the side and the opposite of plus or minus. So we want Z star times the square root of p hat q hat over n. Okay, for 95%, okay, I kind of know that's 1.96. You can check that by simply doing the inverse norm of 0.025, comma 0, comma 1, and you're going to get negative. The Z star is always going to be positive, so that's why I make it that. So my margin of error is going to equal 1.96 times the square root of p hat, which is going to be 0.49 times q hat, 0.51, divided by n, which is 799. All right, and when you do that for part A, you end up getting 3.5%. So that is the answer for part A. So B, explain what this margin of error means. So it means the following. The pollsters are 95% confident that the true proportion of teens who have misrepresented their age is within 3.5% of their estimated 49%. Okay. C, if we only need to be 90% confident, will the margin of error, this is not D, be larger or smaller? And explain. So for 90% confidence interval will result in a smaller margin of error. If the confidence is decreased, a smaller interval is constructed. So let's find that margin, okay? So again, it's gonna be Z star, but for 90%, the Z star is gonna be 1.645. So we have 1.645 times the square root of 0.49 times 0.51 over 799. And that is going to give us 2.9%. Indeed, it was smaller. So in general, if all other aspects of this situation remain the same, would smaller samples produce smaller or larger margin of errors? So the answer, smaller samples generally produce larger intervals. Smaller samples are more variable, which increases the margin of error. Okay. Example 6. First USA is a major credit card company is planning a new offer for their current cardholders. The offer will double airline miles on purchases for the next 6 months. If the cardholder goes online and registers for the offer to test the effectiveness of the campaign, First USA recently sent out offers to a random sample of 50,000 cardholders, of which 1184 registered. All right, so A, we're going to give a 95% confidence interval for the true proportion of those who registered. All right, so for part A, before we do that, let's go through this whole process. Okay, so we have to check some conditions here. The first condition we have to check, do we have a random sample? Okay, and the answer to that is yes. It says it was sent to a random sample of 50,000 cardholders. All right, the next one, 10%. We have to assume, this is true, that's going to be more than 500,000 cardholders. Okay. All right. Now let's check NP hat. And when I do that, I get 1,184. And NQ hat, I get 48,816. Both are greater than or equal to 10. Okay. So we have a great answer. Now, let's go ahead and calculate this. So first step is taking our P hat, which is going to be 1184 divided by 50,000. Okay, so our confidence interval is P hat plus or minus Z star times the square root of P hat Q hat over 50,000. So if I'm doing this all by hand, it's going to be 1184 over 50,000 plus or minus 1.96, that corresponds to the 95%, times the square root of 1184 over 50,000 times 48,816 over 50,000 divided by 50,000. And when we do that, we end up getting 2.23% to 2.5%. And that is my confidence interval for part A. All right, part B. If the acceptance rate is only 2% or less, the campaign won't be worth the expense. Given the confidence intervals you found, would you say that? Okay. So the confidence interval gives the set of plausible values with 95% confidence. Since 2% is outside the interval, 2% specifically is right here, there is evidence that the true proportion is actually higher than 2%. So the company should be worth the expense. So if the acceptance rate is 2% or less, the company won't be worth it. Ours is going to be higher than that. So it is worth the expense. Now what I want to do is I'm going to share my screen with you so I can show you a shortcut on the calculator. All right, so I'm going to share my desktop now instead of just that. Okay, and I'm going to bring up my calculator. And I'm going to show you a quick shortcut on how to calculate this confidence interval. Okay. Right. So what you could do here to calculate this value, instead of typing all of this in by hand, is simply going to stat and going over to tests. And then what we're going to be calculating is something called a one proportion z-test, one prop z-test. You hit enter there. All right. I'm sorry, that's not a z-test. Quit. It's a one proportion z interval. Okay, so we want to find one proportion z interval, which I believe is option A, but let's find that. And there it is, one proportion z interval. Okay, so our x value was 1184. Our n was 50,000. And our confidence interval was 95. Now, you have to enter this as a decimal. So 95% becomes 0.95, and then you just hit calculate, and it does all the work for us. There's our 2.23%, and there's our 2.5%. So that's just a much faster way to calculate confidence intervals. All right, so here's example 7. Direct mail advertiser sends solicitations, aka junk mail, to thousands of potential customers in hope that some will buy the company's product. The acceptance rate is usually quite low. Suppose the company wants to test the response to a new flyer and sends it to 1,000 people randomly selected from the mailing list of over 200,000. They get orders from 123 of these recipients. Okay, so let's create a 90% confidence interval for the percentage of people who the company contacts and what they want. I'm just going to do the shortcut and go straight to the calculator. So I'm going to go to stat, I'm going to go to tests, I'm going to go to alpha A, which is one proportion z interval. All right, so we get 123 for my x. We send it to 1,000. Okay, we want a 0.90 confidence, and there's my answer. Now, remember, our answer is not sufficient. Before I calculated this, I have to check my conditions. Okay, so for our independence assumption, there's no reason to believe that one randomly selected person's response will affect another's. Randomization condition. The company randomly selected 1,000 recipients. The 10% condition. 1,000 recipients is less than 10% of the population of 200,000. So notice we have a finite population. We have to check the 10% condition. All right, our success failure condition. So n times p hat is 123 and n times q hat is 877. Both are greater than 10. So since the conditions are met, we can use a one proportion z interval to estimate the percentage of people who will respond to the flyer. Now, if I'm writing my answer, I would have written all that up along with my final confidence interval, which is going to be 10.6% to 14.0%. So this final answer is really minimal. You actually have to check your conditions and state what you're about to perform. We are about to perform a one proportion z interval. Okay, so B, explain what this interval means. So I would write the following sentence. We are 90% confident that between 10.6% and 14.0% of the people will respond to the new flyer. All right, C, so explain what 90% confidence means. So what that means is about 90% of random samples of size 1,000 will produce intervals that contain the true proportion of people who will respond to the flyer. And then D, the company must decide whether to now do a mass mailing. The mailing won't be cost effective unless it produces at least 5% return. What does our confidence interval suggest? So our confidence interval suggests that the company should do the mass mailing. The entire interval is well above the cutoff of 5,000. Now, this is a lot of writing, and if you look on Haiku, I posted my Google Slides link, and in the notes for the Google Slides, you can actually see all of the answers written. Okay. All right, so this I think should be example 8. So the mayor of a small city has suggested that the state locate a new prison there, arguing that the construction project will result and resulting jobs will be good for the local economy. So a total of 183 residents show up for public hearing on the proposal, and a show of hands finds 31 in favor of the prison project. What can the city conclude about the public support of the mayor's initiative? Okay, now this is kind of a trick question. So for this answer, I would have said the following. So many of you would want to immediately write our confidence interval because you have numbers and you would want to go to the calculator. You know, you have to stop and think, okay? So the city council can conclude nothing about general public support for the mayor's initiative. Okay, those who showed up for the meeting are probably a biased group. In addition, a show of hands vote may influence people, affecting the independence of the votes. So if your data is faulty, your conclusions are going to be faulty. Remember that. We spent the whole chapter or the part discussing the proper ways to collect information. So even though you have the numbers and you could calculate the confidence intervals, we just can't do it. This information is bad. Okay. All right. So a city ballot includes a local initiative that would legalize gambling. The issue is hotly contested, and two groups decide to conduct polls to predict the outcome. The local newspaper finds that 53% of the 1,200 randomly selected voters plan to vote yes, while a college statistics class finds 54% of 450 randomly voters select to support. Both groups create 95% confidence intervals. So A, without finding confidence intervals, explain which one will have the larger margin of error. All right, so here's part A. The interview based on the survey conducted by college statistics class will have the larger margin of error since the sample size is smaller. Okay, B. So let's find the confidence interval for both samples. All right, so before we do that, we have to check the conditions. Step 1, independence. There is no reason to believe that one randomly selected voter's response will influence another. Both samples are random, and both are probably less than 10% of the city's voters. Okay. So if I check the NP hat and NQ hat for all of them, for the newspaper's poll, the NP hat is 636, NQ hat is 564. For the stat class, NP hat is 243, and NQ hat is 207. So all the expected successes and failures are greater than 10, so the samples are large enough. So since the conditions are met, we can use a 1 proportion Z interval to estimate the proportion of city voters that support the gambling initiative. All right, so again, I would go to the calculator, and I'm going to do these 1 proportion Z intervals. All right, so we go to tests, proportion. So we're going to do the local newspaper first. Okay, now X is P hat times N. So we're going to do 0.53 times 1,200. Okay, and we get 636 out of 1,200. So this is very important. You have to type in an X, and we want 95%. All right, so the confidence interval for the newspaper is going to be 50.2% to 55.8%. And then the confidence interval for the stat class, again, we go to stat, tests, 1 proportion Z interval, and then we do 0.54 times 450. We get a whole number, hopefully, and we have 450, and then 95%. And then the confidence interval for the stat class is 49.4% to 58.6%. So which group concludes that the outcome is too close to call? So the statistics class should conclude that the outcome is too close to call because 50% is in their interval, whereas the newspaper, 50% is outside of their interval. And that is all for this video. You can now begin working on your homework.